Every airline crew trains for engine failures on takeoff. The scenario is drilled so often that the call-outs and control inputs begin to feel almost automatic. What they do not train for is what happens on this afternoon in Chicago, an engine that does not just lose thrust, but rips away from the wing and takes pieces of the airplane's nervous system with it. On May 25, 1979, a fully loaded McDonnell Douglas DC-10 lines up on runway 32R at Chicago O'Hare, bound for Los Angeles as American Airlines Flight 191. It is a clear day, with long weekend traffic building and visibility out to 15 miles. Nothing about the weather hints at trouble. From the terminal windows, some passengers' families watch the large tri-jet taxi. The DC-10 was designed to move hundreds of people across a continent in one hop, its 3 General Electric engines promising redundancy and power. To travelers, it looks like progress in polished aluminum, hidden in the structure, though, is damage no one in the cockpit knows about, a weakness at the junction that holds the left engine and its pylon to the wing. That weakness has been growing quietly over weeks of groundwork. In a few seconds of takeoff roll, the crew will believe they are facing a familiar emergency, one they have studied in checklists and simulators. Yet the airplane will be in a completely different kind of crisis, one the procedures did not really contemplate. The paradox at the heart of Flight 191 is simple and troubling. How can following a practiced engine-out profile still leave a modern airliner uncontrollable? The answer lives in the details of speeds, systems, structure, and a maintenance shortcut that seemed efficient at the time. Flight 191 is a routine domestic flight on paper American Airlines, 3-engine DC-1010 Chicago O'Hare to Los Angeles. The aircraft, tail number N110AA, has over 11,000 flight hours behind it, maintained under a system vetted by the airline, the manufacturer, and federal regulators. It carries 258 passengers and 13 crew members, all qualified and medically fit for duty. That afternoon, the weather is benign. Reports show clear skies and surface winds from the northeast at about 22 knots. Runway 32R, more than 14,000 feet long, offers ample distance for the performance numbers the crew has calculated. On the takeoff data card, V1, the critical decision speed after which a rejected takeoff is no longer considered safe, is set at 139 knots. Rotation speed, VR, is 145 knots. V2, the target climb speed with one engine inoperative, is 153 knots. The stabilizer trim and flap settings are set according to company procedure. Everything matches what the manuals prescribe. In the cockpit, the captain, first officer, and flight engineer work through the final checklist. Maintenance personnel standing near the gate and along the taxi route see nothing abnormal during engine start and pushback. The airplane's 3 engines spool up, smooth and symmetrical, their instruments steady in the green. From an operational perspective, the flight launches with no unresolved defects, no weather constraints, and no obvious reason to expect anything but an uneventful climb toward the west. Yet somewhere deep in the left wing, the metal that anchors the number 1 engine pylon has already been stressed beyond what the original design intended. The way the engine was recently removed and reinstalled faster than the factory method has left microscopic evidence of that stress. No one in the cockpit has seen that evidence. The oversight systems meant to catch such issues have not flagged it. The airplane starts its takeoff roll with a structural vulnerability that will matter exactly when the crew is most committed to flight. At 14:59 local time, Flight 191 taxis from the gate toward runway 32R. The crew receives taxi and then line up clearance like thousands of flights before them. At 15:02:38, the tower clears them for takeoff. 8 seconds later, the captain responds, American 191 underway, and advances the thrust levers to take off power. The airplane accelerates, weight shifting from its tires to the lift building over its swept wings. On the runway, the speed calls come steadily. The engines reach their planned power setting. The instruments show normal parameters. As the tri-jet approaches V1, the point of decision, there is still no sign in the cockpit of what is about to happen. The captain hears the first officer's V1 call. At that moment, By doctrine and training, the takeoff is committed. Even if one engine fails, the crew will continue the roll and fly the airplane away on the remaining thrust. A rejected takeoff at this speed would carry its own serious risks. Just seconds later, the crew reaches VR. The captain gently pulls back on the control column, initiating rotation. This is the moment where several invisible factors converge the loads on the left engine pylon peak. The air loads on the leading edge slats change rapidly, and the minimum speeds for directional control and lift intersect with the commitment not to stop. For observers near the runway, the sequence looks suddenly and violently wrong. They see pieces of structure separating from the left engine area, a brief burst of vapor or smoke, and then the entire number 1 engine and its pylon assembly break away from the wing, flipping over the top before falling to the runway. Inside the cockpit, the crew likely experiences this as abrupt yaw and vibration more than a visual event. Cockpit voice recorder data shows normal callouts up to the point where the recording abruptly stops, coincident with the loss of power from the left engine's generator. In an instant, the flight crew moves from a normal takeoff into an emergency that shares some symptoms with a standard engine failure, but hides something much more complex: damage to hydraulics, uncommanded changes in the wing's lift devices, and the loss of several key instruments and warnings. Flight 191 lifts off roughly 6,000 feet down the runway, initially climbing with wings level. From the tower cab and nearby roads, witnesses see the DC-10 climb to just over 300 feet above the ground. For a few seconds, it looks as though the trijet is performing a standard engine-out climb, heavy but still very much airborne. The right and tail engines continue to deliver takeoff thrust. From a pure thrust perspective, the airplane still has power to fly. The real problem is not simply missing thrust. When the number 1 engine and pylon separate, they tear through hydraulic lines routed in the wing and rip away about 3 feet of the left wing's leading edge. Those hydraulic lines normally help keep the leading edge slats locked in position. With the lines severed, the outboard slats on the damaged wing retract on their own as the airplane accelerates and climbs. The right wing keeps its slats deployed, maintaining high lift. The left wing suddenly loses a crucial part of its lift-enhancing devices while still at a low speed and high angle of attack. In the cockpit, this slat retraction is not directly obvious. The instruments that would indicate slat disagreement and stall warning are powered from systems fed by the missing engine. The loss of the engine and its generator occurs at virtually the same instant that the airplane needs those warnings the most. Some of the normal cues that would tell the crew that the left wing is now aerodynamically different simply never appear in front of them. As the captain pitches for the company-mandated V2, the combination of high angle of attack, asymmetric slats, and missing engine creates a deadly situation. The left wing reaches its stall angle while the right wing is still lifting efficiently. The aircraft begins a roll to the left. The crew attempts to counter with aileron and rudder, but the forces are overwhelming. The roll rate increases, the nose drops below the horizon. Within seconds, the wings pass through the vertical. The airplane, now partially inverted and descending, is no longer controllable within the normal flight envelope. 31 seconds after liftoff, Flight 191 impacts an open field near a trailer park north of the runway end. The wreckage scatters into the trailers and an old hangar. Fire erupts immediately. All 271 people aboard and 2 on the ground lose their lives. 2 additional people on the ground are injured. It is, at the time, the deadliest aviation accident in United States history. To understand why Flight 191 became uncontrollable so quickly, it helps to look at the airplane as a system of balances. An airliner at takeoff is not just a machine accelerating down a runway. It is a carefully arranged compromise between thrust, lift, drag, and controllability. Remove one engine, and the system is still designed to function. Speeds like V1 and V2 are chosen so that, even with a failed engine, rudder authority and wing lift are sufficient. That is the logic behind engine-out training. But Flight 191 never experiences a textbook engine failure. It experiences a structural failure that changes the shape and behavior of one wing while simultaneously silencing key warning systems. The slats on the leading edge of a wing act like extending the edge of a book's page downward to catch more air at low speeds. On the DC-10 with slats extended, the wing can generate high lift at lower speeds without stalling. When the outboard slats on the left wing retract without the crew's command, it is as if that part of the wing suddenly reverts to a cleaner, higher stall speed shape while the rest of the airplane is still configured for liftoff. The result is asymmetric lift. One wing is operating near its limit, the other still has margin. At the same time, the DC-10's design routes some of the stall warning and slat disagreement logic through systems tied electrically and hydraulically to the very engine that has separated. The NTSB later finds that the loss of the engine leads directly to losing those cautions. From a performance standpoint, the speeds the crew use are valid for a simple engine failure, but not for an engine plus slat asymmetry event. The crew's pitch to V2 profile, drilled in simulators and backed by manuals, makes sense when the wings are symmetric. With one wing's slat suddenly retracted, that same pitch attitude pushes the left wing past its stall angle. Engineers later confirmed through simulation and wind tunnel work that at the time and speed of liftoff, the margin between normal operation and an asymmetric stall is extremely thin once the slats retract. Below all of this sits the structural question, why did the engine separate at all? The pylon that holds the engine to the wing is meant to withstand the loads of takeoff, turbulence, and engine thrust with safety margins. Investigators discover that the pylon's aft bulkhead has been weakened by prior maintenance. In search of efficiency, the engine and pylon had been removed and reinstalled as a combined unit using a forklift, rather than following the more time-consuming manufacturer method of separating them. That shortcut introduces subtle bending and cracking where the pylon meets the wing damage invisible in daily operations, but devastating at the exact point of maximum stress during takeoff rotation. The physical chain of events is only part of the story. The human factors surrounding Flight 191's last minutes are just as important. In the cockpit, the crew confronts a sudden yaw and roll at a moment when their workload is already high. They are low, heavy, and committed to flight. Their training tells them that after V1 an engine failure means continue the takeoff, pitch for V2 and climb away. Their company procedures reinforce that pattern. When the left engine separates, the cues they receive fit that known script: a surge of yaw, instrumentation changes, and, for a brief instant, vibrations. There is no obvious enunciation for engine and pylon departed the wing and damaged the slat system. The cockpit voice recorder cuts out almost immediately after the separation, so investigators have only a few seconds of audio to analyze. Still, they conclude that the crew likely believed they were executing a standard engine-out departure. The loss of stall warning and slat disagreement indications robs them of some of the cues that would normally signal an impending stall. The roll they face is faster and more aggressive than expected, and at only a few hundred feet of altitude there is almost no time to diagnose a non-standard emergency and invent a new response. Beyond the cockpit, human factors extend into the hangar and the offices where procedures are written. The decision to adopt an alternative engine pylon removal method is rooted in schedule pressure and efficiency. Removing the engine and pylon as a single unit saves time and avoids the complex rigging associated with separating them. On paper, it seems like a clever solution to maintenance downtime. In practice, it places heavy structural components on a forklift whose deflections and positioning tolerances can load the pylon in ways the designers never intended. This is planned continuation bias applied to maintenance once a shorter procedure appears to work a few times. Organizations may continue using it without fully re-evaluating the risks. Regulators and the manufacturer are also part of the human landscape. Pre-accident reports of prior pylon damage incidents on other DC-10s exist, but the sharing of those findings is incomplete. Surveillance and communication channels between operators, the manufacturer, and the Federal Aviation Administration do not surface the emerging pattern quickly enough. The NTSB later notes deficiencies in oversight and in the intolerance of existing procedures to a unique emergency that falls outside the narrow band of what training and manuals assume. After the crash, investigators face an enormous task. The wreckage field in the open area and trailer park northwest of the runway is both burned and fragmented, But one fact is immediately obvious. The number one engine and its pylon are lying on the runway, far behind the main impact site. That physical separation confirms what witnesses described. This is not a simple in-flight fire or ordinary engine failure. It is a structural breakup under takeoff loads. The NTSB reconstructs the sequence using flight data recorder traces, the brief cockpit voice recorder segment, radar, and structural analysis. They determine that Flight 191's takeoff roll is normal until just before rotation, when pieces of the left engine pylon begin to break away. During rotation, the entire engine and pylon assembly separate as a single unit, taking with it a section of the left wing's leading edge. The airplane lifts off, climbs to about 325 feet, and then begins the fatal left roll and descent. Simulations show that once the slats retract and the aircraft is flown at its standard engine-out climb attitude, an asymmetric stall develops rapidly. Attention then shifts to the pylon itself. Metallurgical examinations reveal fatigue cracks and overload failures in the pylon attached structure. Investigators trace the origin of that damage to maintenance work performed weeks earlier. American Airlines, along with some other operators, has adopted a procedure that removes the engine and pylon together using a large forklift. This procedure is not the one recommended in the original McDonnell Douglas manuals, which call for removing the engine from the pylon first. Under certain misalignments, the forklift method can impose bending loads that damage the pylon's aft bulkhead and fittings. The NTSB's final report concludes that the probable cause of the accident is the asymmetrical stall and ensuing roll resulting from uncommanded retraction of the left wing outboard slats and the loss of stall warning and slat disagreement indications, themselves caused by maintenance-induced damage that led to separation of the number one engine and pylon assembly at a critical point during takeoff. Contributing factors include the vulnerability of the pylon-attached design to maintenance damage, the vulnerability of the slat system to asymmetry, deficiencies in FAA surveillance and reporting, and weaknesses in how operators, the manufacturer, and regulators shared information about previous incidents. This investigative thread closes the earlier gaps. The crew did not mishandle a standard emergency. They faced a scenario where the airplane's systems and structure did not behave as their training assumed. The warnings that might have alerted them were lost at the moment of greatest need, and a maintenance shortcut had set the stage weeks before they ever stepped into the cockpit. The impact of Flight 191 reaches far beyond the immediate tragedy. In the short term, the DC-10 fleet faces intense scrutiny. The Federal Aviation Administration suspends the aircraft's type certificate for a period while regulators and the manufacturer evaluate the design and maintenance practices. Airworthiness directives and service bulletins are issued to address pylon-attached structures and to mandate inspection and correction of any similar damage across the fleet. Operators are instructed to abandon the combined engine pylon forklift removal method and revert to procedures that avoid placing unintended loads on the attach points. Beyond structural fixes, the accident drives changes in how systems are routed and how warnings are designed. Engineers and regulators look again at the placement of hydraulic and electrical lines to reduce the chance that a single structural failure can simultaneously disable both critical control surfaces and the instruments that report their status. Stall warning and configuration disagreement logic are reviewed so that multiple, independent sources can provide alerts when something unusual happens to lift devices. The idea is simple: if a wing suddenly changes configuration on its own, the crew should know, and the warning should not depend on power from parts that could be lost in that same failure. Procedurally, airlines and training organizations refine how engine-out departures are taught. The importance of recognizing abnormal roll or control responses even when speeds and profiles look correct on paper is emphasized. Crews are reminded that procedures are built on assumptions. When an airplane does not behave as expected, immediate attention to attitude and bank angle must take precedence over chasing assigned speeds. From an oversight perspective, Flight 191 prompts a hard look at how maintenance innovations are vetted. The accident underlines that any shortcut or alternative method must be evaluated not only for efficiency, but for structural consequences. Regulators and manufacturers tighten channels for sharing information about near misses and damage findings, seeking to identify weak patterns before they become fatal chains.
But if you go to
The
section
disaster
4.3,
becomes a case study
yes.
in how a
if we
complex
include
system
that
can
statement.
drift into unsafe territory when efficiency, communication gaps, and design vulnerabilities align. Looking back, the story of American Airlines Flight 191 is not just a story of 31 seconds after liftoff. It is a chain that begins in a hangar, continues through approval processes, design decisions, and oversight, and only reveals its full shape in the air over Chicago. The initial curiosity how a crew can follow a practiced engine-out profile and still lose control is answered by the combination of engine pylon separation, uncommanded slat retraction, and the loss of the very warnings designed to guard the edge of the flight envelope. The question of why the airplane rolled so violently despite having two working engines resolves into the concept of asymmetric lift, one wing configured for high lift, the other suddenly cleaned up, both asked to carry a heavy airplane at a steep climb attitude. The mystery of why the crew did not recognize the deeper structural failure lies in the silent instruments. When the generator on the missing engine went offline, it took critical indications with it, and the disturbing link between a maintenance shortcut and a catastrophic accident becomes clear in the cracked metal at the pylon attach points, stressed by a forklift-based procedure that seemed harmless until it was not. Out of this comes a set of sober lessons. Redundancy is only as strong as the independence of the redundant paths. Training profiles must be understood as conditional, not absolute. Maintenance efficiency must never outrun structural understanding. Oversight must be alert not just to checklists on paper, but to how real-world practices evolve on the line. Flight 191 leaves an imprint on aircraft design, regulatory practice, and training philosophy that continues to shape aviation decades later. The skies above Chicago look no different today, but the rules and expectations that govern the aircraft passing overhead bear the mark of what was learned in that field north of runway 32R. Every time a wide-body aircraft accelerates down a runway now, it does so in an environment subtly altered by what investigators learned from Flight 191. The passengers see only seats, windows, and a distant horizon. But behind the scenes there are redesigned structures, revised procedures, and a deeper respect for how small decisions on the ground can affect safety in the air. This documentary has walked through those 31 seconds and the years of choices that led to them, not to sensationalize tragedy, but to understand and remember. If you want to keep exploring how aviation learns from its hardest days, consider staying with this channel, sharing what you have learned here, and joining the ongoing conversation about flight safety. Thank you for watching, and for caring about the details that keep modern air travel as safe as it is today.